Let's come now to the second part. We will discuss so-called scale types. We differentiate 4 different types of scales: a nominal scale, ordinal scale, an interval scale, and a rational scale. The different scales differ in terms of what kind of operations and comparisons are possible on values of these different scales. From top to bottom, more operations and more comparisons are possible. On the other hand, it's not as easy to find something which is measurable on a rational scale as it is on a nominal scale. We need to understand the differences in scale in order to understand how can we manipulate values that are measured on these different scales. This is, I think, best understood in the specific cases. Let's have a look at the first scale, nominal scale. What is it? It's basically a set of values. The only operation or relation that is supported on those is equality, meaning I can determine whether two measurements measured in a nominal scale achieve the same value or a different one. I cannot say anything else. Examples could be a so-called defect class. That would be an interface defect, a control flow defect, etc. Then for different defects, I can say, well, they come from the same class or not. Well, there is no comparison in the sense of larger or smaller. I cannot add or subtract these kind of classes. Now, all of these operations are not allowed. That's why it is a nominal scale. The second one is an ordinal scale. And what we will see from scale to scale is the later scale always subsumes the former scale, meaning everything I can do for a nominal scale, I also can do if something is an ordinal scale, but something comes on top of it. Yeah? So what is an ordinal scale? It is basically an ordered set of values. While the nominal scale was just a set of values, now it is ordered. That means beyond a quantity, it is also meaningful to define an order in the sense of something is larger. Yeah? A typical example could be software complexity. We could measure software complexity in terms of low, medium, high, very high, whatever, different categories. And then, of course, if something falls into the category of medium, it has a larger complexity than something that falls in the category of low. And if something falls in the category of high, it has a larger complexity than if something falls in the category of medium, and so forth. Yeah? So these different complexities can be compared. They are larger than relation. However, I cannot simply subtract or do other operations on those. And this is the important part. I could also call software complexity, and instead of calling low, medium, and high, I could call them 1, 2, and 3. So I would give them a number, then still subtracting the numbers just wouldn't make a lot of sense. And that is why it is an ordinal scale. Yeah? So don't be fooled. If something is expressed as numbers, it does not automatically mean that typical operations you know from numbers, like addition, subtraction, multiplications, really make sense. However, this is a very common problem that I have something ordered, and actually I would like to do operations like differences, subtract, meaning subtracting, and so on. This is only possible if the distance between two of the classes has always more or less the same amount in some meaningful way. Yeah. For that reason, so-called Likert scales are sometimes used. They are not truly interval scales, but they can be approximately used in this way. You find that very often if people do interviews. They exist in a number of different varieties, either with odd number of entries or with even numbers of entries, depending on whether there is a neutral point or not. And a typical Likert scale would be something like strongly disagree, disagree, neutral, agree, strongly agree. And the idea is, and people try to calibrate it in just this way, that the difference between what people mean with a strongly disagree and a disagree is in some sense similar to the distance between a disagree and a neutral. So from that perspective, one could use it as an interval scale, meaning one could do more than just what is possible for an ordinal scale, but still I would recommend to be very, very careful with that. If people provide questionnaires, they also give like sketches where there are explicitly numbers assigned to these positions or lines added to enforce that there's some equidistance. This is all more or less useful, but it's not, or it's never guaranteed that you can really use that as an interval scale. So it may look like something like you see here on the right hand side. We have here different questions from a website user survey, and then we have different marks, and we try to emphasize that this distance is like that distance. If we really have equidistance among the individual elements, then we actually come to an interval scale, meaning the interval between two different values is always the same. So an interval scale is an ordered set of values where the difference between values is meaningful and constant. What does meaningful mean here? It means that there is some interpretation of this distance, of this difference between two values, that makes sense in the domain. For example, let's look at temperature. The difference between 1 degree and 2 degree, you may not be able to state right away, but there's a physical interpretation of what that means. And in that sense, it's always the same difference between 1 degree and 2 degrees Celsius. It's the same as between 30 degrees and 31 degrees Celsius. So this is another example, actually, of an interval scale. Operations that are possible on the interval scale are already pretty plenty. So we have equality again. We also have ordering, meaning we can compare them. But we also have now addition, subtraction, mean. We can even do standard deviations. We can do correlation, regression, analysis of variance, transformations like linear combinations, a times x plus b, etc. All of these are correct operations on an interval scale. An example for that, beyond the Celsius scale that I just mentioned, would be a difference in defects of some modules. The last scale we want to look at is the rational scale. This is the most powerful scale of all four. In this case, an absolute zero exists, and the ratio of two measurements has actually a meaning in the domain we are talking about, meaning it's reality. So we could talk about something like half the temperature. And I will return to that in a moment, because half the temperature is not necessarily what you would expect it to be. So the operations here are all of those which we have from the interval scale. As I said earlier, each of the later scale always subsumes everything of the former scale. In addition, the rational scale supports geometric mean, harmonic mean, coefficient of variation, and logarithms. Examples for that would be lines of code. There's clearly an absolute zero. It makes sense to talk about twice as much lines of code. Same for number of defects detected, working hours, etc. All of these are rational scales. Here you basically have all of the possible operations for mathematics that you know, basically. In the real world, for example, the temperature scale of degrees Celsius is not necessarily, or is not really, a rational scale. There is a temperature scale which is meaningful as a rational scale. That is the scale Kelvin, which you may know from physics. So let's do a small exercise. Classify the following scales. Which operations are supported by the scales, and therefore which scales are those? Here are the questions. The colors red, green, and blue. The RGB values, these are color values, color coding that is used for computers. Degrees Celsius, which I already mentioned, so you got some hints. Time, already hinted at that as well. School degrees. Now pause for a moment, and only when you have your own answers, return to the video again. Welcome back. So here we are. The colors red, green, and blue, we have as operations equality. Nothing else. Two different colors I cannot compare meaningfully as larger or smaller. In that sense, it's a nominal scale. There's a subset of colors with which I could also do an ordering. For example, these would be the rainbow colors. There are physical reasons why that would make sense. But if I take arbitrary colors, it's basically equality, and that's it. RGB values are basically the same thing. They are not even ordered in a meaningful way, as you see here with the example. So is this smaller or larger than that one? Hard to say. That doesn't make a lot of sense. We can say they are equal or not, but that's it. So it's again, operation is equality, a nominal scale, no ordinal scale. The next one, degrees Celsius. It definitely has ordinal capabilities, but I also can do subtraction. So the difference between minus 10 degrees and 0 degree is in a physical sense really the same as between 0 degree and 10 degrees. So it's at least an interval scale. But would it be a rational scale as well? And the answer is no. There's no absolute zero. The reason is, in the Celsius scale, 0 is arbitrarily fixed to the freezing point of water. There is no deeper physical meaning to that. As I mentioned earlier, the Kelvin scale would be a rational scale. That has an absolute zero, and that, however, can be translated into Celsius. And if then we do, for example, half the amount of temperature, which corresponds to half the amount of energy, then an interesting result comes about. Let's take as an example plus 25 degrees Celsius, which is a very nice temperature. In Kelvin, that's roughly 300 degrees. If we have half the temperature, that's now not 12 degrees Celsius, but that's roughly 150 degrees Kelvin. And how much is that in Celsius? It's like minus 120. So that's not just cold or freezing cold, that's extremely cold. So having the absolute scale leads to very different results than one would expect in a different scale. So Celsius is an interval scale, nothing more. Time, if we measure a time span in terms of 10 minutes, 20 minutes, etc., then we can have equality, we can divide that, there's an absolute 0 point, so we have a rational scale. So that's nice as well. The last one, the school degrees, is actually a pretty interesting one. The fact that this is at least an ordinal scale, I think, is pretty clear. Somebody achieving a 1 is better in the sense of what's measured by the school degrees than somebody achieving a 2, who in turn is better than somebody achieving a 3. So far, so good. But for the next scale, for the interval scale, the question is, are those different marks really equidistant? Meaning, do we have the same difference between somebody achieving a 2 as we have versus somebody achieving a 3 as we have between somebody achieving a 1 and a 2? So are these the same interval in a meaningful sense in terms of what the school degrees are measuring? And that's actually a question that is pretty rarely asked, and I would say it often is not the fact. So in that sense, well, equality is clear, a larger comparison is also clear, subtraction does hardly seem to make so much sense. So an ordinal scale, we can easily use it. An interval scale, not so easy to argue. And now think at something like all the reports on your final exam sheet, where basically interval operations are done, like average marks are given, and this pretty clearly shows this is at least a questionable approach.